Denise Huddle here. We're going to hit on some basic chemistry. You've heard these terms before, like matter, solids, liquids, and gases, but here are some definitions. When we talk about energy, we need to differentiate between kinetic energy and potential energy. So kinetic energy is the idea of energy in motion. Energy is doing work, something's moving. For example, maybe a windmill is turning. That's kinetic energy. Potential energy is energy that is stored. Think of the Mactaquac Dam or another dam you might know, where a great deal of water is held back and not moving at this time. But we know that there's a lot of energy stored in that water, because if we allowed it to move, it would turn some turbines, and then that would become kinetic energy. The best example of chemical energy in the body is in ATP, adenosine triphosphate. It stores energy. When it breaks down to adenosine diphosphate, ADP, and 1-phosphate group, then it releases its energy. So you can see that that energy was stored in a chemical form. Electrical energy results from the movement of charged particles. We're going to look at that when we look at how energy moves along a neuron. And mechanical energy is involved with moving matter, like moving our biceps, for example. And then radiant energy travels in waves. We actually use this type of energy with radiant warmers to keep newborn babies warm when they're having difficulty keeping themselves warm. We know that matter is made up of tiny things called elements. There are numerous types of elements that are listed on the periodic table, but the most common elements in our body are oxygen, carbon, hydrogen, and nitrogen. In fact, they make up 96% of our bodies. Atoms are the building blocks of elements, so atoms combined can form elements. And they are different from each other. We're going to study them now. They're composed of subatomic particles termed protons, neutrons, and electrons. And protons have a positive charge, electrons have a negative charge, and neutrons are neutral. They do not have any charge. So we've learned about the charges of the subatomic particles, but also we should appreciate that the protons are assigned one atomic mass unit for their mass, and neutrons also have one atomic mass unit for their mass. Electrons essentially have no atomic mass unit. It's negligible, so we consider it to be zero. Atoms are neutral because the number of protons equals the number of electrons, and their charges cancel each other out. Ions, on the other hand, are atoms that have lost or gained electrons. Therefore, they either have a positive or negative charge. This is the depiction of an atom using the planetary model. The planetary model portrays the atom as a little solar system. It shows the protons and neutrons in the nucleus in the middle. They are shown, the protons are in red here, the neutrons are in yellow, and see how they're in the nucleus. The electrons are shown in orbitals around the nucleus. We can see them as smaller and little blue balls. In this case, we're looking at a helium atom. It has 2 protons, 2 neutrons, and 2 electrons. The planetary model is a little out of date, but is still used for ease of comprehension. The orbital model of studying an atom is a bit more modern day, and the electrons are depicted by an electron cloud. It's a haze of negative charge outside the nucleus, and the electron may be anywhere in that cloud. We just don't know exactly where it is. We still have the protons and neutrons shown in red and yellow, and they're inside the nucleus. The atomic number indicates the number of protons in the atom. The atomic mass number is the number of protons plus neutrons in the atom. The atomic weight is the approximate weight of the mass. It's going to be slightly different than the atomic mass number because of the idea of isotopes. And isotopes mean that the atom can exist with slightly different numbers of neutrons. So we know that a neutron has a weight. So if the atom is existing with a different number of neutrons, then it would have a slightly different weight. So if most of the atoms have an atomic mass of 10, but one of them has an atomic mass of 11, the average of them is the atomic weight. So it could be slightly different. Here is the definition of isotopes. It mentions that they are atoms that have the same number of protons and electrons, but they vary in their number of neutrons. And these isotopes They do have the same atomic number, but they have a different atomic mass. And when we average all of them together, they make the atomic weight slightly different. Here is an excellent example of isotopes. Here we have hydrogen, as it typically presents, with 1 proton, no neutrons, and 1 electron. An isotope of that is called deuterium. It has 1 proton, 1 neutron, and 1 electron. Tritium is another isotope of that, and it has 1 proton. As we see, it has 2 neutrons and 1 electron. Some of these isotopes are very unstable, meaning that they won't stay in that state for very long. They have a tendency to emit their neutron and decay. Some isotopes are used in nuclear medicine. For example, with the PET scanner uses an isotope that has a short half-life, let's say about 6 hours, and it has a great ability to go into the body and go out to the areas with a high metabolic rate. These areas of a high metabolic rate are often cancerous areas, and these areas will light up when the patient is x-rayed. This is sort of a basic overview of how a PET scan works. So what I want you to understand is sometimes isotopes are used medically in nuclear medicine. Here we go. So a molecule is 2 or more atoms that are the same that have joined together. So we see an example of that, 2 hydrogen atoms joining together to form a hydrogen molecule. And here we go with a compound. Compounds have 2 or more atoms that are different, and they join together. For example, we have 4 hydrogens and 1 carbon joining together to form methane. Methane is a gas. Electrons exist on electron shells. The first shell typically holds 2 electrons, the second shell can hold a maximum of 8 electrons, and so on. The bonding of, or the sharing of electrons between 2 atoms only occurs with the outermost shell. The inner full shells are unaffected. Atoms with full valence shells do not form bonds. That means if their outer shell is perfectly full, it does not connect or combine with any other atoms. It's content. Here we have 2 noble gases, helium and neon. They are termed noble because their outer valence shell is complete. Therefore, the atom is very content. It has no desire to share or give away an electron because its outer valence shell is perfectly full. Helium has 2 electrons in its shell, which is what the first shell normally has, and neon has 8 electrons in its second valence shell, which is what it normally has when it's full. If an atom has an incomplete outer valence shell, it'll have a strong desire to gain, lose, or share electrons with a neighboring atom in order to achieve its goal of having a full outer shell. In some cases, one atom will completely give an electron to another atom to achieve stability or achieve full outer shell valences. In this case, we call that an ionic bond. This slide is heavily weighted on tests. When an atom gives away an electron or gains an electron, it now has a charge. So it's called an ion. Specifically, the type of ion that has a negative charge because it gained an electron is called an anion. And the type of ion that has a positive charge because it lost an electron is called a cation. I always remember that because cation has a T in the middle that looks like a positive. Once this occurs, that one atom has given an electron to another and now they each have a charge, they have a tendency to be attracted to one another because of their opposite charges. Those 2 atoms are drawn to each other. This is an excellent example of an ionic bond. What has happened here is that the sodium atom started out with 1 electron in its outer shell. It's a very undesirable situation. It does not want to have just 1 electron in its outer shell. It wants to give up that electron, so its outer shell is the one underneath, which has 8 electrons. The chloride atom started out with 7 electrons in its outer shell, which made it very unhappy because it has a desire to have a full valence shell on the outside and to have 8 electrons. So sodium gave an electron to chloride in order to achieve their goal of having full outer valence shells. But once that was done, now sodium has 1 less electron, so it becomes a positive cation, and chloride has 1 extra electron, so it becomes a negative anion. Now that these things, they're called ions now because they have a charge, now they have opposite charges and they're drawn to each other, and we call that sodium chloride or salt, table salt. In some cases, atoms decide simply to share electrons to make themselves feel like they have full outer valence shells. In the case of a single covalent bond, 1 pair of electrons are shared. We're going to see that next. And in the case of a double covalent bond, 2 pairs of electrons are shared. The hydrogen atom has 1 lonely electron in its shell. That is not what it wants to have. It wants to have 2. So what it often will do is join with another hydrogen atom to form hydrogen gas, H2, and they share these 2 electrons, and it makes each hydrogen atom feel as though it has a full outer valence shell. This is called a single covalent bond. Now here's a very important molecule for us to know, oxygen, O2. So let's look at the oxygen atom by itself. It only has 6 electrons in its outer shell. Of course, it wants to have 8. So what it decides to do is join up with another oxygen atom and share 2 pairs of electrons so that each atom feels as though it has 8 electrons in its outer shell. So this forms oxygen gas, or O2. This is called a double covalent bond. This is a little bit more complex. What we have here are we have some different atoms that are going to join together to form a compound, actually, because it's 2 different atoms. What this is going to do is actually have 4 single covalent bonds. The reason is because the hydrogens each have 1 electron in their outer shell and they want to feel like they have 2. The carbon has 4 electrons in its outer shell and it wants to feel as though it has 8 in its outer shell. So they join up and hang out together and have these 4 single covalent bonds where they share electrons 4 times in order to achieve that goal of having a full outer valence shell. In a polar covalent bond, the electrons are not shared equally between the atoms. They're shifted off in one direction a little bit. Because the electron has a negative charge, it makes the molecule have a positive side and a negative side. A really good example of this is water. We're going to look at that next. Here it is. Here is water, and it is considered polar because what happens is where the hydrogens are located have a bit more of a positive charge, and where the oxygen is located has a bit more of a negative charge. So we see then this structure has different charges on different sides of it. So building on that idea of having polarity or charge in our molecule, we can then have hydrogen bonds. These, as it says, are very weak bonds. They're formed when the hydrogen atom, which has a positive charge, is attracted to the negative side of another molecule. And there's just a little bit of attraction there, and it actually causes surface tension. When we overfill a cup of water and it forms a little bubble on the top because of surface tension, this is due to hydrogen bonds. Also, if we see a little water spider being able to walk across the surface of the water, it is due to hydrogen bonds. Synthesis reactions are just like what they sound like. They're also called anabolic reactions, where atoms or molecules combine to form larger and larger, more complex molecules, and decomposition is the opposite. A great example of synthesis reaction is amino acids being built together to form a protein. And a good example of decomposition reaction is ATP breaking down into ADP and phosphate. An exchange reaction occurs when synthesis and decomposition are both happening and there's a switching off of molecules. So this is a great example here. We have AB plus CD equals a new molecules, AD and CB. So there's a switching off of atoms. So what affects chemical reactions? Well, increased temperature and increased concentration of particles will increase a chemical reaction. Also, presence of enzymes or catalysts will increase a chemical reaction if they're the right enzymes or catalysts for that reaction. And smaller particle size atoms actually will have more quick chemical reactions. In chemistry, all of our compounds are divided out into inorganic or organic. In most cases, inorganic compounds lack carbon, and in most cases, organic compounds have a carbon atom within them. There are a few other details listed here as well. Salts or ionic compounds contain a cation, anything other than hydrogen, and an anion, anything other than hydroxide. And they join together, but they are easily dissociated in water or break apart in water. They are very important in our body. For example, there's movement of sodium and potassium across the cell membrane in order for a nerve impulse to pass along a neuron. So that's a very good example. We'll be talking about that and building on that lots more. All salts are considered to be electrolytes, and electrolytes are ions that conduct electrical currents. In this case, water is being used as a solvent. What is happening is we have a salt crystal, that's sodium chloride, shown on the left in green and yellow. It has been put into water, which is acting as a solvent, and the ions are breaking apart into solution. Sodium and chloride are floating freely in the water. When acids dissociate, they release hydrogen ions. An example is hydrochloric acid. This is actually produced in your stomach, believe it or not. Hydrochloric acid can break down into hydrogen and chloride, and it is a strong acid. It tends to ionize completely and release all of the hydrogens. Weak acids ionize incompletely. That means they don't break down completely. Bases are similar. They are electrolytes that dissociate in water and release hydroxyl ions, OH negative. An example is shown here. We can also have strong bases or weak bases, the same idea as with the acids. In some cases, an acid and a base can join together in an exchange reaction and create neutralized products, water and salt. pH is a very important concept. We think of it as representing the number of hydrogens in a solution. The scale is 0 to 14, neutral is 7. Low numbers like 1 or 2 indicate a very acidic environment and a great deal of hydrogen. Higher numbers, closer to 14, are considered more basic and have lower numbers of hydrogen. Here we see that neutral is considered 7, which is interesting. In our body, neutral is actually 7.4, so it's a little bit different. Also, interesting point here is that gastric juices have a pH of approximately 2, so that's a very acidic environment, a high number of hydrogen ions.